So I want to talk about our last algorithm of this unit, Kruskal's algorithm. This, much like Prim's algorithm, is for building a minimum spanning tree, but it has a slightly different focus. Prim, the focus is on vertices. So our priority queue is all about vertices. With Kruskal's algorithm, its focus is on edges. So we'll have a priority queue of edges, essentially. Okay, so as usual, I'm going to take a quick look at the Wikipedia article on it. So again, it kind of describes when it was discovered or popularized and who did it. The basic algorithm creates what's called a forest of trees. So we start off with each individual vertex representing a tree. And whereas Prim's algorithm builds a single tree that gets bigger and bigger and bigger, Kruskal's algorithm starts by building possibly small trees and then joining these small trees together. Okay, so we'll essentially start off with this set F, which is each individual vertex. There will be a second set S that contains all of the edges. So that would actually be our priority queue. And we'll continue processing until either S is empty, we've removed all of our edges, and while we have not yet spanned all of our graph. So if we get to the point where we've got leftover edges, but we've managed to span our graph, we can go ahead and stop. So you might notice that this also kind of follows the pattern of a greedy algorithm. It's continually removing an edge with the minimum weight from our set of edges. And then it does a check to see if it can combine that with our solution. So if the edge connects two different trees, so another way of thinking about that is if the edge doesn't create any sort of a loop, then it will add the edge to our solution set and join together those two trees. Okay, to get a more concrete sense, you can look at the example graph here. I'm going to go through the same problem that we've done a couple of different times, but this time using Kruskal's algorithm. Okay, so we've got our familiar graph. In order to help me keep track of things, I'm going to go ahead and write all of the edge weights down at the bottom. Basically, these will kind of represent the concept of my priority queue. So I'm already just going to go ahead and think about them in order. Okay, so I'm going to go ahead and process these in order. The two 200s, it's kind of arbitrary which one is which. I'm just going to assume that this one is the first one. So again, initially we think of all of these as being independent trees. Each vertex is a tree unto itself, and once I remove an edge from my priority queue, I'm kind of joining together two trees into a larger tree. So now I've got this tree over here that represents Boston to New York, JFK. My next 200 will also be removed. So we have to check and make sure we're not creating a cycle. And I wasn't, so I'll go ahead and join it. So now I've got a tree with size 3. Okay, and our next edge is 300. So this is where we really see a departure from Prim's algorithm. So whereas Prim's algorithm continually grows the single tree, Kruskal's algorithm is actually going to start with this second tree over here. Again, it's not forming any sort of a cycle, so we'll join together those two subtrees into a larger tree. Next up, we've got a 600. I'm going to assume it's this one. Again, that's not forming a cycle, so I'm going to go ahead and join it together. Our next 600, oh, that would form a cycle. So this is one of the cases where we essentially discard this and don't include it in our solution. Okay, we continue through our priority queue. We've got a vertice of size 700. So that's this one here. It also forms a cycle, so we'll also ignore it. Next up, we've got a vertex of 800. So that won't form a cycle. We'll go ahead and make this tree that's growing over here even bigger. Continuing on, we've got a 900. Again, that's also part of this tree over here, so it's getting bigger yet. And then we've got several different 1100s. I'm just going to kind of arbitrarily pick them. I'm going to assume that maybe This is our first one, so that would in fact form a loop. So we'll discard that. I'm going to assume that our second one is right here. That does not form a loop. It joins together this tree over here with this tree over here. So we'll go ahead and include that. The next 1100 would be up here. Oh, it looks like that would form a loop, so we'll ignore that. Next up, we've got a 1400. Oh, by the way, we've got our early stopping criteria. We've joined together all of the vertices. So we can go ahead and stop. And if you remember, this is one of the example minimal spanning trees that we've seen before, or at least it's comparable to one of them. We can add up our edge weights and confirm that we have yet again achieved our minimum. Okay, so I'm going to wrap up by talking about the complexity of Kruskal's algorithm. So first off, we've got the first phase where we somehow get a priority queue or have the edges in order. If we use our best comparison-based sort, that would be n log n, where in this case, we've got the number of items as our number of edges. So number of edges log number of edges would be one approach. Then we've got the second phase of Kruskal's algorithm, the loop that goes through all of those edges, slowly building up the subtrees until we have a single spanning tree. It might have to process all of the edges in order to do that. So as we're going through that loop, if you remember, we have to check that adding a particular edge does not lead to a cycle. So that's a topic that we haven't actually talked about so far, but there is a way to approach it that's not too bad. You can actually check that the two endpoints of the edge that you're trying to add aren't already in the same subtree. Okay, so that can actually be done with an operation referred to as a union find, and it has a known time complexity. So we'll base the rest of this discussion on the fact that we're using this union find, and it's based on the number of vertices that we have to check to see if the endpoints are in the same tree. And at most, we will have v vertices in our tree. When we're all done, we will have created our spanning tree that spans all v vertices, so this is kind of our worst case, and we're slowly, incrementally getting closer and closer to this. Okay, so we've kind of got these two phases. We've got this phase here, and we've got this phase here that is done possibly for each individual edge. Okay, so our total combining those two pieces together is number of edges times log number of edges plus number of edges times log number of vertices. So for simple graphs, we can actually show that the number of edges is less than v squared because we can't have multiple edges connecting the same two vertices. And if we're thinking about in terms of big O notation, so we could kind of substitute the log of the number of edges with the log of the number of vertices squared, because it has to be smaller than that. And then, of course, using our rules of logs, we can actually transform this into 2 times the log of v. Okay, so if we kind of combine together that the substitution, this replacing the log of e with the log of v squared, which can also be replaced with 2 times the log of v, if we combine together those two substitutions, we can come up with an overall complexity of number of edges times log of the number of vertices. Okay. So essentially 2 times number of edges log number of edges, but again we're substituting the log of the number of vertices, which will be an upper bound on the log of the number of edges. Okay, so so just to kind of compare that with Prim's algorithm, again, if we've got a spanning tree, we can actually make some assumptions here. We know with the spanning tree that the total number of edges has to exceed or be equal to the number of vertices minus 1. Otherwise, a spanning tree just isn't possible. So for simple graphs, we could also simplify the time complexity of Prim's algorithm to be the same expression. It's based on the number of edges times the log of the number of vertices.